Okay, let's actually start working through our examples from today's class. So the first thing I've asked you to do is to sketch the graph of f of x equals 2 to the power of x minus 3. For these graphs today, we're moving beyond just our basic sketch. I want you to find all axes intercepts. So we're going to have to do some work to find the x-axis intercept and the y-axis intercept. And I also want you to state what the domain and range is for each of these graphs. So let's work through that problem now. First thing, we've got a base number of 2, and it's an exponential graph, and we also know that it has been translated down 3 places. Please be careful, just remember this is our base number, it's not a dilation factor. For a dilation factor, I'd have to be multiplying that 2 by some other number. I'm not doing that, so it's just the base graph of 2 to the power of x, the base exponential 2 to the power of x. There's no reflections. For a reflection, I would need a negative up here or a negative out the front. So I've only got that translation of 3 units down. So if we start working with our base graph, our base exponential graph of 2 to the power of x looks something like that. And it's got an asymptote at y equals 0. If I don't have any dilations and I don't have any reflections, the only thing I have is this translation of 3 units down. All that's going to do is move my whole graph, and I start by sketching the asymptote. It's going to move the whole graph down 3 places. The intercept was at 0, 1. The intercept, if it goes down 3 places, will now be at 0, negative 2. You can find this as well by substituting x equals 0, but let's save some time and not worry about it. And the base shape looks something like that. We can see in this graph we also have an x-axis intercept. I'm going to do that last. Before I do the x-axis intercept, let's talk for a moment about the domain and the range. So my domain is all of the possible values that x can be. My graph is going to continue forever this direction. My x values are going to go on forever all the way to negative infinity. And to the right hand side, although my graph's going up, I know that it's going to be moving across and across and across. It's going to eventually go all the way to positive infinity as well. So x approaches positive infinity, x approaches negative infinity on the left hand side. So my domain goes from negative infinity all the way to infinity. Or I could just write this as all real values. My range, on the other hand, let's change colours for the range. My range never drops below this asymptote. It also never equals the asymptote. So my range is going to be every value that is greater than negative 3. So it's going to be greater than negative 3. So my range goes from negative 3, notice curved bracket because it doesn't equal negative 3, all the way up to infinity. And infinity always has a curved bracket. Okay, so the last thing I've got to do now is find the x-axis intercept. Now we know from our previous topics that the x-intercept occurs when y equals 0. So let's substitute that into our equation. We get 0 equals 2 to the power of x minus 3. Standard solving processes here. The first thing I'm going to do is the opposite of minus 3, which is to plus 3. So I get positive 3 equals 2 to the power of x. And then normally, when I try and solve this equation, my first step is to try and get the same bases. Can I get the same bases? No, I can't. One's a 3, one's a 2. They're already prime numbers. There's no way these are going to become the same base. So my only way to get out of this problem is I'm going to use my logarithms. All right, so for my logarithms, remember that format. So we've got the base to a power equals a number, or log of the base to a power is equal to the number. So the base to a power, let's get my highlighter out, the base to a power equals a number. The base to a power equals a number. Same thing, different format. So we're going to rewrite my log like this. What does that look like in our expression? Well, it becomes log to the base 2 of 3, the number, equals the power, which is x. Now, we've got x by itself. So that means I have my x-axis intercept. If we're working without a calculator, I can't simplify that any further. So when I write my x-intercept on my graph, I'm just going to simply say this is the point that is equal to log to the base 2 of 3, and the y value is 0. And we list our coordinates as a logarithm, just like if we have surds and square roots when we've had some other problems when we worked with quadratics. Okay, that's the first example. Let's have a look at the second example quickly. Same idea, a little bit different. So example 2, sketch f of x equals 5 times 10 to the power of x minus 4. Okay, exactly the same deal as what we have seen in the past. Notice my base number is 10. This time I absolutely have a dilation factor. So this graph's been dilated by a factor of 5 from the y-axis. So let's work through this as a little bit of a quick sketch. We know that my graph, my normal graph of 10 to the base x looks like that, and it has an intercept at 0, 1. If I dilate by a factor of 5 from the x-axis, everything gets bigger, makes it grow quicker. That intercept that was at 0, 1 will now be at 0, 5 because it's 5 times bigger. The dilation of 5 does not change the asymptote. The asymptote will still be at y equals 0. But then as we continue to move down the line of elements, we now have a minus 4. So that's going to move my graph down 4 places. And we can see that in the asymptote goes down to y equals negative 4. That intercept, if I go down 4 places, will be at positive 1. So it will be at 0, 1, which means my graph has to grow like that. And we can see that we've got an x-axis intercept, and that x-axis intercept should be a negative number now. So let's go ahead and let's do the domain and range first, like we did last time. So the domain, same thing again. My graph's going to continue forever to negative infinity, and it's going to go the other direction to positive infinity. So my domain is r, all real values, and we'll find that's pretty consistent with all of our exponential graphs. Unless there's been a restriction set, the domain will be r. And the range, well, we can see from our asymptote that my graph is everything above negative 4. So my range goes from negative 4 to infinity. We've already got the y-axis intercept. Again, we could have found that by substituting in x equals 0. I'm going to do that this time just to show you. So it'd be 5 times 10 to the power of 0 minus 4, which is 5 times anything to the power of 0 is 1. So 5 times 1 minus 4, 5 minus 4 equals 1. The x-intercept is when y equals 0. So I'm going to actually squeeze that into this space over here, hopefully, so that we can not scroll down and keep looking at that graph and thinking about it as we go. So I'm going to have 0 equals 5 times 10 to the power of x minus 4. Move the 4 to the other side, it becomes a positive 4. 5 times 10 to the power of x. Opposite of times by 5, we're not undoing the power yet, is to divide by 5. So we get 4/5 equals 10 to the power of x. And we get to this space now where we do not have the same bases. This 4/5 is never going to be a base of 10. All right, we can't turn them into the same base. We have to use a logarithm. So we're going to write our logarithm. It's going to be log to the base is 10, of a number. The number is 4/5 equals the power is x. So now we've got our x-axis intercept. You could split this up using a log law, but you don't need to. This is perfectly fine to write your x-axis intercept just like this. Now, so my x-intercept is log to the base 10 of 4/5, comma, and 0. Now, how on earth does that become a negative? This doesn't look like a negative. There's no negative sign there. So we have to think about this a little bit more logically. I know, let's for a moment think about this log. It's saying, let's just write over here, log to the base 10, 4 over 5. What does this equal roughly? I'm working without a calculator. I know 10 to the power of 0 equals 1. This number is less than 1. Okay, so it's less than 1. I know 10 to the power of 1 equals 10. I'm absolutely less than that. So my x value, when I talk about my powers, my power has to be smaller than 0 to become a number that is smaller than 1. So what are the numbers that are less than 0? They're the negative numbers. So although we have no negative sign in here, because this number that we're trying to get as the answer is less than 1, the only way I'm going to achieve that is through a negative power. Therefore, this expression is actually negative, although there's no negative sign shown. So my final graph looks like that. And that's the end of the example.